Just 2 months ago, a major scientific discovery was announced.
Ladies and gentlemen, we have detected gravitational waves. We did it.
This detection was solid evidence of something Albert Einstein predicted 100 years ago. But it was also the most direct observation ever of black holes.
The discovery of gravitational waves has launched a new era in the study of perhaps the most captivating and powerful objects in the universe.
In science fiction, spaceships often go through a black hole to another universe, or another part of our universe. But black holes are stranger than anything dreamt up by science fiction writers.
Tonight, we're joined by Stephen Hawking to take a mind-blowing journey into the enigmatic world of black holes.
We're going to find out how the astonishing discovery of gravitational waves, made just a few weeks ago, is already helping us understand the fundamental nature of them. In a truly extraordinary life, Professor Stephen Hawking has become the world's most celebrated scientist.
And for over 40 years, he's wrestled with the toughest of questions. What happens inside a black hole?
Black holes are formed by the collapse of massive stars when they have exhausted their nuclear fuel and can no longer support themselves against their own gravity. They are quite literally holes in space that stuff can fall into, but not get out of. They are places where the gravitational field is so strong that nothing, not even light, can get away.
This basic picture of black holes is very well known. But unfortunately, it is also far from complete.
At the heart of the mystery of black holes lie two fundamental problems.
Firstly, theorists have found it hard to understand what's happening inside a black hole. In fact, the more they crunch the numbers, the more it seems that black holes defy the laws of physics. In particular, it throws up a mind-boggling conundrum known as the information paradox.
Secondly, astronomers trying to observe these unusual objects and find physical evidence with which to test these theories hit an apparently insurmountable problem. You can't see inside a black hole.
The maths don't add up, and no one's ever seen inside a black hole. So how do we know they even exist? Also, what kind of discovery can hope to answer all of these mysteries?
Well, with the help of Professor Hawking, we're going to try and answer all of those questions.
So we've come here to the University of Cambridge, home of Stephen Hawking and arguably the birthplace of black hole science.
In tonight's programme, we'll hear from Stephen Hawking himself, how he transformed our view of black holes.
Black holes were thought to be completely black, until I discovered that they glow like hot bodies.
I'll be finding out from cosmologist Andrew Ponson why Hawking's black hole theories created one of the biggest conundrums in astrophysics.
With Hawking radiation, very slowly, a black hole gradually shrinks away until it's completely gone. There's no trace of the Earth, no evidence that it ever really existed, let alone what it was made up of.
And I'll be meeting one of the team behind the wonderful discovery of gravitational waves, exploring what they tell us about black holes.
We know its mass. We also know that it's spinning. It's spinning about 100 times a second. We know it's about the size of Iceland. It's not spherical, it's actually an ovoid.
But we'll start with that astonishing discovery of gravitational waves.
Unravelling the secrets of the universe, the most important scientific discovery for a generation. Scientists in the United States have announced they have discovered gravitational waves.
Einstein was right after all. Gravitational waves ripple through space and time.
The discovery of these elusive waves is the end of a search that began with Einstein's work 100 years ago. But it's also the beginning of a new way of seeing what had previously been invisible in the universe, revealing remarkable objects like black holes. The idea that black holes might exist was suggested here in Cambridge as far back as 1784. The Queen's College don John Mitchell was fascinated by the idea of extreme gravity, and he imagined that a big enough star might generate a gravitational pull that was so intense not even light could escape. John Mitchell called these objects dark stars, and he realised that we couldn't ever see them directly, but he thought we might be able to detect them by watching for their gravitational effects on objects around them. Sadly, his 18th century colleagues ignored him, and dark stars were lost to the world for the best part of 200 years.
That is, until the arrival of Hawking and a new wave of black hole physicists. They were intent on understanding some of the surprising implications of Einstein's theory of general relativity. When physicists began to explore Einstein's theory of general relativity, they found that it made all sorts of bizarre predictions, and one of the weirdest was the existence of black holes. To see how black holes were predicted by general relativity, you need to get to grips with a concept at the heart of Einstein's theory: space-time. Einstein insisted that time and three-dimensional space weren't actually separate at all, but they were woven together into the four dimensions of space-time. What's more, space-time was distorted by mass, just as this ball distorts my sheet, causing a curved dip. Just as our dip causes a second ball to roll towards it, distortions in space-time cause objects to fall together. And that is what we feel as the pull of gravity. This curving of space-time elegantly explains how planets and spaceships orbit around a large mass. It also reveals they can only overcome that pull and escape from orbit if they can travel fast enough to make it all the way up the side of the hole. Pretty straightforward so far. But things get interesting when you consider really dense objects, the sort of thing that cosmologists consider result from the death of a giant star. If it was massive enough, a star like this would collapse under its own gravity, and according to general relativity, form a singularity. A speck of infinite density at the centre of a bottomless pit in space-time. In order to escape the steeply sided curve of a hole like this, you needed to be travelling faster than the speed of light. Now, nothing can travel that fast, so nothing, not even light, can escape a hole like this. A black hole. But even though general relativity implied that black holes should exist in theory, most physicists didn't much like the idea. It raised awkward questions like what would happen to things once they'd fallen in. And besides, the sort of dense collapsed star that you need to produce a black hole had never been observed.
But then, in 1967, astronomers here in Cambridge discovered the first pulsar, an object powered by a collapsed dense star, the first hint that such objects really existed. And suddenly, black holes were back on the agenda. Here at Gonville and Caius College, a young Stephen Hawking took up the challenge to take a fresh look at black hole theory. And right from the start, he managed to make waves.
Black holes were thought to be completely black, until I discovered that they glow like hot bodies, with a temperature that is higher, the smaller the black hole. This points to a deep and unexpected connection between black holes and thermodynamics, the science of heat.
The trouble was, how could heat be coming from a black hole? Nothing should be able to escape a black hole. Hawking suggested a new form of radiation, consisting of strange particles that exist in the bizarre world of quantum theory.
Quantum mechanics implies that the whole of space is filled with pairs of virtual particles and antiparticles that are constantly materializing in pairs and then annihilating each other. Now, in the presence of a black hole, one member of a pair may fall into the hole, the other particle may fall after its partner, but it may also escape to infinity, where it appears to be radiation emitted by the black hole.
This mind-boggling concept is now known as Hawking radiation. And with it, Stephen Hawking had solved the problem of how energy can escape from a black hole.
The trouble is that in solving one problem, it created another, bigger one, the information paradox.
In Einstein's most famous equation, E equals mc squared, he showed that energy and mass are intertwined. So a black hole losing energy must also be losing mass, albeit very slowly.
The radiation will carry away energy from the black hole. The black hole will lose mass and eventually disappear. This creates a paradox, because the information about what fell into the black hole appears to be lost, but the laws of physics say that information can never be lost.
Information's tricky. It's not things like names and stories that can't be lost. Maggie met up with cosmologist Andrew Pontzen to find out what kind of information does cause the paradox.
Information is a critical thing in physics. It's telling us where we are and how we're sitting and what we're made out of. We think of all of that stuff as being information.
So this is the parameters that govern the atoms in the universe?
Yeah, exactly. The idea is that if you know everything about how the universe is today, then you should be able to predict what will happen in the future, or work through the equations backwards and predict what happened in the past. But if you want to be able to do that, then you need this idea of preserving information. Now, the problem is, if you imagine something falling into a black hole, you or me, or maybe just put the whole Earth into a black hole. In fact, I can do that for you right now. Yes. So I take my...
oh, phew, just a piece of paper.
Yeah, no, not the real Earth, just a piece of paper. So I pop it into my black hole over here, for which I'm using a shredder. Now, in principle, if you looked carefully enough inside the black hole, you can imagine you've got some bits and pieces in there.
So we could recreate this and put it back together with a long time and a lot of sellotape.
It would be pretty boring, but you could do it in principle. So the information is still there.
OK, yes.
However, with Hawking radiation, very slowly, a black hole actually reduces its mass. So over time, it gradually shrinks away until it's completely gone. There's no trace of the Earth, no evidence that it ever really existed, let alone what it was made up of.
And you can't retrieve that information in any way?
Exactly. It seems like you wouldn't be able to get at that information at all. So there's no way you could work backwards and work out that the Earth used to exist. It's just gone and lost.
So is there any way to resolve this?
We hope there's a way to resolve it, but right now it's fair to say nobody knows. And people are trying to resolve it in lots of different ways.
Despite 40 years of effort, the information paradox is still unresolved.
If Hawking radiation exists, then we have to solve the information paradox. We have to work out what happens to the information as it falls into a black hole and how they can evaporate without destroying it. If, on the other hand, Hawking radiation doesn't exist, well, then something's fundamentally wrong with our understanding of black holes and perhaps even quantum theory. The problem is that theorists have raced ahead with these ideas about what black holes might be like, but how do we observe that they exist at all? The trouble is, we can never see them directly.
What we can see is some of the evidence that suggests black holes are lurking out there. In fact, some of it is surprisingly easy to spot with a telescope. Pete Lawrence has spent a night on the hunt for black holes.
Various clues have been spotted over the years that seem to signal the presence of black holes. You just need to know where to look.
One area of interest lies in the constellation of Cygnus the Swan, and here there are several pieces of evidence which may suggest the presence of black holes. Now you can currently find Cygnus low in the northeast part of the sky at about 1 a.m. In 1964, one of the earliest space telescopes, a suborbital rocket fitted with a Geiger counter, detected a flood of radiation coming from this part of the sky. And they narrowed the source down to about there and called it Cygnus X1.
On closer inspection, it appeared that this was something incredibly small and compact, producing an extraordinary amount of energy.
Astronomers put forward a theory to explain what they were seeing. What initially looked like a single star actually turned out to be a binary system, a large blue star with an invisible companion.
Could this be a black hole? One explanation for all that energy being released was that gas from the visible star was being sucked towards a black hole, creating immense friction as it spiraled into what is called an accretion disk. As it's heated, that gas would release a colossal amount of energy and even bright X-ray flashes. There are signs of much bigger black holes to look for too.
If we look back at Cygnus, there's an unremarkable patch of sky in the western wing of the Swan. Now, there's not much to see here visually, but astronomers were astounded to see a bright radio source emanating from this region.
The bright signals came from two jets of material spewing out from either side of a distant galaxy at tremendous speeds. Such jets should take huge amounts of energy to produce, like converting 1,000,000 times the mass of the Sun to pure energy, more than the nuclear fusion that drives stars could ever produce.
The only known phenomenon that could convert matter to energy that efficiently was what astronomers had seen in the Cygnus X1 system, accretion. But this must be on a much, much larger scale, so there must be a massive, unseen black hole at the centre of the galaxy.
Bright jets and accretion disks give us enough evidence to suggest similar supermassive black holes exist at the centre of almost all galaxies. But if we look towards the heart of our own galaxy, there's even more compelling evidence.
The centre of the Milky Way galaxy is in the constellation of Sagittarius, which at the moment is more or less behind me. But if you're out on a clear summer evening, then this region of sky can be seen low down in the south. Now, of course, we can't see the supermassive black hole at the centre of our galaxy, but we can see the effect it's having on the stars around it.
For 25 years, astronomers have tracked the motion of stars at the heart of the galaxy. And it's quite clear they're orbiting around something. That something must be over 4 million times the mass of our Sun, squeezed into just 17 times its size.
And that's what we now call Sagittarius A star, our very own supermassive black hole. With all the evidence we've seen over the years, we're pretty convinced that black holes do actually exist. But the next challenge would be to detect one directly.
Until this year, astronomers have relied on this circumstantial evidence to deduce almost everything that we know about black holes.
But all that changed just a few weeks ago with the first direct detection of not one, but two black holes.
It was these black holes that caused the gravitational waves in February's big announcement. Professor Sheila Rowan is one of the team behind the discovery. I joined her to find out more and to see what it all means for black hole science. It's a very exciting time to be talking about gravitational waves, but what exactly have we seen?
What we've seen is space vibrating, space shaking, as picked up by the LIGO observatories in the United States with a device that's about 4 kilometres long, measuring motions 1/10,000th the size of a proton in the nucleus of an atom. So quite phenomenal.
Wow. Incredibly small.
This is the signal that we observed, and what we saw was those vibrations speeding up, vibrating faster and faster to a peak, and then the vibrations die down slightly.
And all of this detail, all of this vibration happens very, very quickly.
It does. It happens in about 0.2 of a second, but amazingly encoded in the vibrations in that 0.2 of a second is information about the source of those vibrations. 2 black holes colliding about 1.3 billion light years away, so 1.3 billion years ago, and arriving with us here on Earth last September. And that speeding up is actually the 2 black holes spiralling in faster and faster until they eventually collide to form a new black hole that then wobbles at a particular frequency, and we can use that again to tell us about the properties of the new black hole that's been formed.
See, this is, to me as an astronomer, the really exciting thing, to be able to make an observation that tells you about the properties of the black hole itself, not about stuff falling into it, but actually about the black holes. So what do we know about the two that merged, and what do we know about the state of the system now?
We can tell the masses of the 2 black holes that merged, and one of them was about 36 times the mass of our Sun. The other one was about 29 times the mass of our Sun. The mass of that final black hole is about 62 times the mass of our Sun. If you add up the initial masses of the 2 black holes that merged in that final mass, you'll discover there's energy equivalent to 3 times the mass of our Sun that has gone somewhere, and where it's gone is into gravitational waves.
Wow.
In a short period, a huge amount of energy is produced, more than the luminosity, the light power of all the stars and galaxies in the observable universe.
Wow.
It's kind of amazing.
Okay, so what else do we know about this newly formed black hole?
We also know that it's spinning. It's spinning about 100 times a second. We know it's about the size of Iceland. It's not spherical, it's actually an ovoid. It's kind of squished in one direction, stretched in the other slightly, spinning away. So, and all of that we can get from this signal that we detect in gravitational waves. And this is the first time we've been able to do anything like that.
I think the most remarkable thing is not just the signal, but the fact that it represents a huge amount of effort by a lot of people, most of whom laboured for years without ever detecting anything. How does it feel to be sitting here describing a real signal?
It feels amazing, and it's the first time we've seen these binary systems. They might never have existed, and the black holes merging is the birth of a new black hole. That's a unique signature that we see, that we really couldn't see any other way, and so that's really fantastic.
This is incredibly exciting, but it's just one detection. So what's next?
It's just one detection, but we can combine that with our models for how the universe is, and that lets us calculate possible rates of these events, how many we might expect. I mean, it could be anything from a few a month to 1 a day. And so that's phenomenally exciting, that we may see a whole population of these events out in the universe.
And that's just from these 2 detectors?
That's just from these 2 detectors, that's right. These are just part of a whole potentially new astronomy, using a whole set of different instruments to detect gravitational waves across a wide range of frequencies. And that's very exciting.
So more data coming?
More data coming.
2016 is going to go down in history as a big year for black holes. But now we know that they exist and can even detect them directly. What does that mean for the information paradox and Hawking radiation? Critically, it's an opportunity for Stephen Hawking to test his theories at last. Especially his extraordinary idea that when black holes combine, they make one new one with more surface area than the first 2 put together.
The signal LIGO detected came from the collision and merger of 2 black holes in a black hole binary. This should make it possible to experimentally test my prediction. The area of the horizon of the final black hole is greater than the sum of the areas of the original holes. This prediction is crucial to our understanding of the thermodynamics of black holes.
By making sense of their thermodynamics, LIGO and its successors could provide the first experimental evidence that black holes do glow with Hawking radiation. But could there be more direct evidence, out at the very edge of the observable universe, the cosmological horizon?
LIGO is not sensitive to the wavelengths at which there is appreciable Hawking radiation from black holes. However, there is likely to be another kind of Hawking radiation of much longer wavelength coming from the cosmological horizon, which might be detected by radio telescopes.
Long-wave radiation like this would have to come from a type of black hole formed right after the Big Bang, in the early primordial universe. It would be a unique kind of gravitational radiation.
I hope that radio telescopes detect primordial gravitational radiation from the cosmological horizon. That would mean black holes almost certainly emit radiation, and would get me a Nobel Prize.
If Hawking radiation can be proved to exist, then there must be a solution to the information paradox, and Professor Hawking thinks he's found that too. He believes that objects falling into a black hole leave the information they carry behind. It's stored on the hole's surface, which becomes turbulent, a process called supertranslation.
Last year, I realized that a black hole can store the information in what is called supertranslations of the horizon. I am now working with my colleagues, Malcolm Perry at Cambridge and Andrew Strominger at Harvard, on whether this can resolve the paradox.
If he's right, Stephen Hawking has solved one of the greatest mysteries in cosmology. But does that mean you can escape from a black hole after all? Or would it still be bad news to fall in one?
Definitely bad news. If it were a stellar mass black hole, you would be made into spaghetti before reaching the horizon. On the other hand, if it were a supermassive black hole, you would cross the horizon with ease, but be crushed out of existence at the singularity.
Well, there's no doubt in my mind that with the detection of gravitational waves, the future of black hole science looks bright.
And after 50 years of theoretical debate, Stephen Hawking might get the experimental evidence he wants to test his ideas about black holes. And there's another exciting project on the horizon too, the Event Horizon Telescope, a worldwide network of radio telescopes that next year will team up to try and capture the first image of the shadow cast by the enormous black hole at the Milky Way centre.
This would have been unimaginable when Stephen Hawking started grappling with black holes over 40 years ago. But it shows that this is another chapter in the history of black hole science.
Next month, we'll be previewing one of the astronomical highlights of the year, the transit of Mercury, visible across the UK on May the 9th.
And we'll be using the opportunity to take a closer look at Mercury, one of the strangest planets in the solar system. To find out how to catch a glimpse of it before then, check out the website for Pete's April Star Guide. In the meanwhile, get outside and get looking up.
Good night.
Coming up here on BBC4, we're off on a mission to Mars with a Horizon special in just a moment.